You ever look at an ancient artifact in a museum, a piece of papyrus or a prehistoric bone, and just wonder, how do they know it's thousands of years old? Well, it's not magic and it's not a guess. It's science. And today, we're going to pull back the curtain on radiocarbon dating, the amazing tool that lets us literally listen to the echoes of the past. So here's our roadmap. We'll start with the basic problem, how do you tell time? Then we'll get into the brilliant idea of the cosmic clock. We'll see how scientists actually read this clock, deal with all the messy real-world problems that try to mess up the results, and then, this is the really cool part, how they calibrate it all to give us a precise history. It's a journey that literally changed everything we thought we knew. Okay, so let's dive in. For anyone who studies the past, the number one most important question you can ask about anything you find is, how old is it, right? Because without a reliable date, a beautiful pot or an ancient tool is just, well, it's just a thing. Its story is totally lost. I mean, think about something like the Dead Sea Scrolls. These are, without a doubt, some of the most important historical texts ever found. But when they were discovered, how could anyone be sure they were really from 2,000 years ago and not some elaborate fake from the Middle Ages? Well, the answer, it lies inside a tiny, unstable atom. And that brings us to the cosmic clock. See, back in the late 1940s, this chemist, Willard Libby, had an idea. And it was one of those ideas that was so elegant, so profound, it would end up winning him the Nobel Prize. He realized that nature itself had built a secret timepiece into every living thing on Earth. Now, the key to this whole thing is an atom called carbon-14. Most of the carbon in you, me, and everything around us is good old stable carbon-12. But way, way up in the atmosphere, cosmic rays from space are constantly slamming into nitrogen atoms, and every now and then they knock one just right and turn it into a slightly heavier, radioactive version of carbon. That's carbon-14, radiocarbon. And here's where it gets so cool. This special carbon-14 mixes with oxygen to make carbon dioxide. Plants breathe it in, animals eat the plants, so every living thing, from a giant redwood tree to you and me, is constantly taking in a tiny, steady amount of this radiocarbon. We're in perfect balance with the atmosphere. But the second an organism dies, that all stops, it's not eating, it's not breathing, the clock starts ticking. No new carbon-14 is coming in, and the carbon-14 that's already there starts to decay at a perfectly predictable rate. And that predictable rate, it's called the half-life. It takes exactly 5,730 years for half of the carbon-14 atoms in a sample to disappear. Poof, they turn back into nitrogen. Then it takes another 5,730 years for half of the remaining atoms to disappear, and so on, like clockwork. So if you can measure how much carbon-14 is left, you can calculate exactly how much time has passed since that thing died. It's genius. So the theory is beautiful, right? It's so elegant. But actually measuring it? Oh, that's a whole different ballgame. We are talking about trying to count a ridiculously tiny number of atoms in a sample. It's a huge technical challenge. The original way they did this was called beta counting. You basically put your sample in a box and you wait for the carbon-14 atoms to decay and count the little particles they shoot out. It was slow, it was imprecise, and you needed a big chunk of your precious artifact to do it. But then came accelerator mass spectrometry, or AMS. This was a total game changer. Instead of waiting for atoms to decay, AMS uses these massive magnets to literally sort through the atoms one by one and count the carbon-14s directly. It's incredibly fast, super accurate, and you can date something as tiny as a single grain of wheat. It completely revolutionized the field. All right, but just when it seems like the science is all figured out, we get a plot twist. It turns out the real world is it's a messy place. And there are a few things that can really throw a wrench in our nice, neat cosmic clock. Problem number one is a big one: contamination. You see, if any carbon of a different age gets into your sample, it's going to mess up the date. A tiny, modern rootlet growing into an ancient piece of wood can make it seem thousands of years younger. And dead carbon, like from a fleck of limestone that has no carbon-14 left, can make it seem way older. We're talking about anything from soil acids to old glues used by conservators, even, and this is a real one, cigarette ash from the original excavation. So how do they deal with that? They have to clean the sample. They have to really clean it. Labs have these incredibly intense pre-treatment processes, using all sorts of physical and chemical washes, like this classic acid-alkali acid routine, to strip away every possible contaminant. The goal is to make sure you're only dating the carbon that was part of the original organism and nothing else. Okay, another weird wrinkle is something called the marine reservoir effect. So the water deep in the ocean is really, really old, which means most of its carbon-14 has already decayed away. As that deep water cycles up to the surface, it mixes with and dilutes the surface water. This means that any creature living in the ocean, a seal, a fish, a seashell, is living in an environment that's naturally low on carbon-14. The result? They'll automatically look about 400 years older than they really are. It's a known offset that scientists always have to correct for. But all of those issues, they kind of pale in comparison to the single biggest complication, the one that made scientists realize the simple calculation wasn't enough. It's the discovery that the amount of carbon-14 in the atmosphere hasn't actually been constant over time. The whole system fluctuates. And guess what? We're a big part of the reason why. In just the last century and a half, we humans have managed to mess with the atmosphere in two huge opposing ways. First, by burning fossil fuels, we've pumped tons of ancient, dead carbon into the air, diluting the natural carbon-14. That's called the Suez effect. Then, in the 50s and 60s, atmospheric nuclear bomb testing did the exact opposite. It created a massive bomb pulse of brand new carbon-14, nearly doubling the amount in the atmosphere for a while. All of this leads to the single most important rule you have to learn about the science. Radiocarbon years are not the same thing as calendar years. A raw date from the lab gives you an age in radiocarbon years, but because the atmospheric starting point has wiggled around so much, that number doesn't line up one-to-one with our actual calendar. So what's the solution? Honestly, it's a thing of beauty. It's called the calibration curve. Scientists have spent decades meticulously dating thousands of things they already knew the exact age of, most famously individual tree rings going back tens of thousands of years. They measure the radiocarbon age of a tree they know is, say, 3,000 years old, and see how far off it is. By doing this over and over, they've built this massive, incredibly detailed correction chart. It's like a decoder ring for the past. Now, a lab gives you the radiocarbon age, and you just look it up on the curve to find the real true calendar date. So, after all that work, after figuring out cosmic rays and half-lives, after fighting contamination and building these incredible calibration curves, we get the payoff. And what a payoff. You see, radiocarbon dating didn't just help archaeology, it blew it wide open. It was a complete revolution. I think this quote from the anthropologist R.E. Taylor just says it perfectly. What radiocarbon data did was create a world prehistory. For the very first time, we had a universal timeline. An event in South America could be directly compared to an event in Europe on the exact same scale. And this new timeline, it completely rewrote the story of us. It gave us solid scientific dates for huge events like the end of the last ice age. And maybe more importantly, it proved a lot of old ideas wrong. We used to think big inventions like farming or pottery started in one place, some cradle of civilization, and spread out. Radiocarbon dating proved that's not true. These were ideas that people came up with independently, all over the world at different times. This one incredible tool has totally reshaped our understanding of where we came from. It took what were basically educated guesses and turned them into a scientific timeline of the human journey. Which, of course, leaves us with one last really exciting question. As the technology keeps getting better and more precise, what other secrets buried deep in the past are just sitting there, waiting for their clock to finally be read?